So basically, something like this would be not differentiable there because the slope on one side does not match the slope on the other. So basically, the quick definition of differentiable is the slope is continuous through the point. So something really simple would be like a value. Slope here is -1, slope here is 1, it's discontinuous then. If I graph the slope here is -1, and the slope here is 1. So the slope is discontinuous at that point. So it's not differentiable at that point. I like it. So, if something is differentiable at a point, that pretty much means it has to go through that point kind of smoothly. Do you guys agree with me? And if I have a function that goes through points smoothly, what's going to happen when I zoom in on this point? What's going to happen to the graph as I zoom in on it?
Straight line.
It's going to become very straight. Okay. And we've done that before. Sort of like I talked about, we're on the surface of the earth. There's actually flat earth people because they think I'm on the freaking thing and it looks flat to me, and it's like being way too zoomed in. Zoom out, holy shit, all the freaking pictures of earth are curved. So, awesome. Now, this is an idea known as local linearity. Locally to that point, it's linear. Okay. So this brings up a very interesting possibility. Bless you. If I have a really disgusting function, but it's differentiable, right? So let's say I have a really kind of gross function, but it's differentiable. Yes? Of course. If I have a disgusting function, but it's differentiable, I should be able to figure out a line that will give me a good estimate for the values around that point. So what do I mean? If I draw a tangent line in, doesn't the tangent line follow the curve pretty closely for a while? Locally, right? The minute I get too far away, the tangent line is way far away from the, look at that, it's way off. But as long as I'm close, the tangent line would give me good estimates for what the actual value is. It may be. So let's do this. I want to do two things in quick succession. I want to do a problem we've done before, and then I'm going to talk about it, recast it in the way that this section puts it. This section makes it sound like it's brand new, and it isn't. But I do want you to get used to kind of like the way they set things up. So what am I talking about? What about the fourth root of x? So if I ask you to find the fourth root of 2, is that easy for you to do in your head? Go. Can you figure out the fourth root of 2? I look, Ricardo's like, no problem, man. What's the fourth root of 2? Go. No. Right? Okay. So let's do this. Let's figure out the tangent line to f of x at 1, 1. Is when I put a 1 in the open. So this is old news, correct? We've done this before. This is one of the most basic things we could do once we learn derivatives. So what do I do to figure out that tangent line? What do I do first, of course? Take the derivatives. Great. So let's rewrite this f of x as what? X to the 1/4. The derivative would be I like it. Remember the shortcut? 1 minus 4 is -3. Okay, now what?
Plug in the x values to get the
Yeah,
slope.
so I want to know the slope, which will be, this guy is the slope formula. It tells me the slope at any point, and I specifically want the slope at 1. And of course, what is that? Don't overthink it. What's 1 to any power?
1.
Times 1/4.
1/4.
Okay, kind of like that, should. So we're almost there. I just got to put it together, right? What's the 2 most important pieces of information I have up here right now to get this? The slope, the point. Yes, I like it. So you forget all the other shit. All the other shit doesn't matter anymore. What do I throw this information into?
Y minus y1 equals m, parentheses, x minus x1.
And let me do this right now. Let me do this right now. Wasn't our y1? Where did I get this from? Isn't this the y? Where did I get that from? How did I get 1? I plugged a 1 in for x. So if I call this a, isn't this f of a? Okay. So this is really f of a. What was m?
M was 1 over 1.
F prime of a. Right? And this would be x minus a. And this will be, we'll put y for right now. Yeah, we'll put y for right now. I can't remember what this book does. We can call it L for the local linearization. We'll call it y for right now. So you're going to see something like this formula. I really desperately want you to realize it's nothing new. How do you get the y? You plug the frickin' x value in. How do you get the slope? You plug the x value into the derivative. Right? This is nothing new. The section makes it look like it's new. So what do we get? We get y minus 1 equals 1/4. X minus 1. So we get y equals 1/4 x. Minus 1/4 plus 1 is plus 3/4. Okay. So let's see, let's test this out. So my claim is this will approximate this. That's my claim, right? This will approximate this as long as my inputs don't get too far away from that. When is this perfect? At 1. In fact, let's try it. If I plug a 1 in, what do I get? I get frickin' 1. It's perfect at 1. Of course it is, because that's where the change line hits. The minute I move away from it, my function is curving away. But as long as I don't get too far away, my approximation should be good. I really want this to make nothing but sense. So 2 is kind of far away. It's not terribly far away from 1. Are you guys kind of with me? Is this function going crazy? Or is it smoother? It's definitely smoother, right? So I should be able to in fact, real quick, what's a 4th root look like? That, right? And I'm at 1, so I got my linear approximation there. So if I go to 2, it should still be decently close. So let's try it. What is, let me call it, I can't remember what this book calls it. I want to call it the same thing. Barf. Oh, they just do that. That's kind of silly. Okay. They just put approximately. Some books put a little L for linear approximation. All right. So y at 2 is approximately 1/4 of 2 plus 3/4. Somebody help me out. What is that? 5/4, 1.25, right? Now, somebody else help me out, or anybody. What am I approximating here then? This function approximates this function. That is a shitload easier to do though, right? Somebody in your calculator, can you do 2 to the 1/4? Let's check it out. 4th root of 2. Let's see how close we got. What is the 4th root of 2? 2 to the 1/4 power. We're doing it live. I have no idea how good this is.
1.189.
1.189?
Yeah.
Not that bad. Not. In fact, if you round, I mean, it's almost the same. Sort of close. Why is it not like crazy close? Because 2 is kind of far away from 1. In fact, we should be kind of familiar with close really does mean close, right? So 2 is a little far away, so my approximation gets worse the further from what I am. So let's get a little bit closer. Let's try y at x equal to 1.1. So this would be 1/4 of 1.1 plus 3/4. Let's make it, hey, real quick, I'm sorry. Make it 1.2, you'll see why. I want to make this something we can do in our head pretty easy. 1/4 of 1.2 is 0.3, is that cool? 0.3 plus 0.75 is 1.05, is that cool? So we can do that in our head. Now somebody help me out. What am I approximating here? The 4 through to what? 1.2. What is the 4 through to 1.2?
1.04.
1.04.
7.
7. Blah, blah, blah. How close are these?
Very close.
So we took a freaking 4th root function and changed it into a linear function. That will work pretty well as long as I stay close. What would I do from the beginning if, let's say for example, I want to know what the 4th root of 17 is? Should I use this work we did? 4th root of 17. What do you think?
No,
Why not?
because it gets further, the answer differentiate more the further it gets from 1.
Exactly. 17 is nowhere near 1, correct? So let's say though that I need to do like the 4th root of 17. How could I, from the beginning, what would I change? What would I change?
The point values.
What would I make this? Not 17, that would suck. What's 17 close to that the 4th root can do all day? 16. So, stay with, how do you guys feel right now? You okay? So it's not a lot new. We're just kind of repackaging what we've done. We know how to find tangent lines. We know how to do that. We kind of know that it was close to the function. From the beginning we kind of knew that. But this is just putting it more in our face. It's close to the function, therefore we can use it to estimate the function. Especially the grosser my function is, the more I want to freaking use a line. Right? Especially if it doesn't matter if I'm off a bit. Okay, maybe. Okay, so let's do this. Let's do this again, but now let's build it around 16. Tangent. Well, now let's just use full. Here we go. Find the linear approximation. At a equal to 16. So when you see an instruction saying find the linear approximation at, that's the same thing as find the tangent line at. So now we can say, let me make this official, the linear approximation will be f of a plus f prime of a times x minus a. Isn't that exactly just y minus y1, I just added it over? Plus equal m times x minus x1. Right, that's all that is. So we know f of x is x to the 1/4. So what's f of a? Let's see. We know f prime, we already did that, is 1/4 x to the negative 3/4. Now here's where things get a little more interesting. What is f prime of 16? Because I need that here, right? So the nice thing with this is it's more constructionist. When you have it in this form, you're like, okay, I need this, let me get it. I need this, let me get it. Whereas this method was sort of like piecemeal. Let me get this, let me get that, let me throw them in. But it's the same it's the same. It's the same process, right? So what is f prime of 16? Can you guys, don't say anything. Try to figure this out. See if you can do it without a calculator. I have faith in you, come on. Right, that's the slope we got before, same function, so now I want to know at 16. Right, you do this. How do you do this in your head? You ready? 4 through to 16 is 2. 2 to the third power is 8. Flip that, 1/8. Right? All this power says is 4 through it, cube that, flip it. And I can do each one of those things in my head with that number, right? What?
And then times 1/4.
Yes. So I get 1/4 times 1/8, 1/32. And what does that tell me? Slope, 11. I like it. All right, so now I can just put this all, now I can just put it in here. Y equals f of a is 2 plus 1/32 times x minus 16. So I got 1/32 x minus 1/2 plus 2. So it'll be plus 3/2. Is that cool? Put up here 16 comma 2. So let's check this real quick. You guys see what I just put down there? Isn't that the point, right? 16 comma 2. How do I check my work? Where is this supposed to be perfect? At 16. So, and when I plug a 16 in, I better get frickin' 2 out. That's where it's supposed to exactly go through and agree with the function, correct? So what do I get when I put a 16 in? 16/32 is 1/2, plus 3/2 is 4/2, which is 2, yeah. So you can always check to make sure you actually get the point you're supposed to. So now let's try, can you guys really quickly use what we just did to estimate the 4 through to 17? Go. Over 32 plus 3/2, which is 17/32 plus 48/32, which is 65/32, which is something 2 and 1/32. 2 and 1/32, which I believe is 2.03 something maybe?
Yeah.
Look at me doing that. You'll see that? Okay. 2.03, whatever. Yes, something close to that? Is it 0333?
0305.
05? Okay. All right. I pushed it too far. And what is the 4 through to 17 actually? My hand is out of batteries.
2.031.
Holy shit! Right? No? Maybe? So on one level it should be like, well duh, of course. But on another level, this is flippin' cool. if you're writing a computer program and you have an approximation instead of a thing, it could reduce your running time, especially if you don't have to be exact, especially if you have like a tolerance level, you can live with it, right? And if you're not going to write computer programs, you're still going to have to do this shit because it's in the homework and so the test. This, what's really neat, in fact, I said this earlier, this is a linear approximation to the data, correct? Right, that's what that is up there. It's a linear approximation to the data. I don't have a function, I have data. But couldn't I have used, I could actually use a quadratic. And I did, and it didn't change much. It was just very slightly curved. You guys, I want you to really with me. Then I could use a cubic function, a fourth power, a fifth power, and every time I do that, it should kind of make it fit the data better. Because it's giving it more to work with, right? If I just try to fit a straight line or something, it's much harder than going, I'll let you curve however you want to. Then it's like, okay, I can do that shit. So what I'm saying is, this is all we have to worry about right now. But we could actually, I could put other stuff on here related to higher degrees, and those would actually make the result curve. Couldn't I fit a curve? So if I have a function like this, and I use a line to approximate it, that's going to kind of suck very quickly, yes? Relatively quickly, it's going to suck. It's like, I'm good, and I suck, right? So wouldn't it be great, what if instead of using a straight line, what if I kind of took something and put a curve on there? Couldn't it match longer? Okay, I like it. That's not what's in this section. If you take, let me see, did we do it this semester? No. That's in Calc 2. If anybody's going to take Calc 2, you will learn you will learn infinite, squared, cubed, fourth power, fifth, and that would fit perfectly. Okay, I'm sorry, I'm pushing this. Okay, I'll stop. All we have to worry about for this section is this. Yes?
What is that the equation for?
This is the equation for the linear approximation. So let me make this more. Given a function, I can approximate it with this line.
That's different than a tangent line.
It's the same thing as a tangent line. It's the exact same thing. So that's why the very first problem I did it not new. It was old shit, right? So find a tangent line. This section repackages this to look like this, so it feels to a student like it's new, which I always kind of hate it. It's a little evil. It's nothing new. We're just being more specific about what's that. Oh, it's what you get when you plug the freaking thing in. What's M? Oh, it's what you get when you plug the thing into the derivative, right? It's the same thing. So here's where things get a little wonky. Doesn't it make sense that the next level of this would be, well, how far away from 16 can I get? Wouldn't that be an interesting question, right? How far away from 16 can I get and still get like something reasonable? Right? That's a good question to ask. All right. I like that some of you guys are agreeing with me because they're going to do that, even if you didn't agree with me. So let me take this away. I'm going to finally graph some stuff. I feel like I've not graphed anything, which is a little weird for calculus, but oh well. So we've got, where's my, there it is. So I have a linear approximation. All right, there you go. And what I want to know is, how do I want to say this? I want to know, when is this approximation, somebody help me out. What do you think would be good? Would it be okay? How far off is it okay for our answer to be? It's like this answer was off by 0.005, roughly, if I remember correctly. Wasn't it like 2.025 or something? I can't remember. So, how much off is acceptable to you? Like 0.1? Is it okay to be off by 1?
No.
No. So what about 0.1? Would that be okay to be off by 0.1? What do you think? Do you guys understand what I'm asking right now? Like if the answer was supposed to be 2.13 and we got 2.03. How do you guys feel about that? Still not good enough? I like the way you're thinking. But let's go with 0.1 for right now. Right? In the real world, it would depend on how bad it is to be how far away, right? So what your tolerance is, if you're measuring radiation levels, do you want your tolerance to be really big? No. I think it's okay. Let's go in. I don't feel good. No, so that's bad, right? But if you're talking about, I don't know, shit, you got water in a pool and it's like 30 feet below the top, your tolerance for how actually deep that water, how tall that water is, it could be off by a couple feet, you'd be fine, right? Does that kind of make sense? Horrible example, but too bad. It's the first thing to know. So let's say we want this to be within 0.1 of the actual value. Cool. Okay, so how do we do this? So what I'm saying is I want, do you remember how to set this up now? Let's see. I want, you can do it, Jeff. Let me think. Yeah, there it is. Okay. I want, I gotta think ahead a little bit. Hold on. Doom. Doom, that's right. Okay, go. So I want this. Let me see if this makes sense. I just had to remember which way. It actually, anyway, it doesn't matter. I could turn it, but it doesn't. I want the result of this and the result of this. I want the distance. Is that cool? Absolute value is distance. Right? You guys know that, right? Absolute value is distance, yes. Did it get a reaction? Absolute value is distance, yes? Okay. So the distance between this and this, I want it to be at most 0.1. Okay. Let's see if you guys remember this. I can write this then. So I can write this then. Now some of you guys are like, yeah, you can write that. Sure, why not? You know, what the shit? You can write whatever the hell you want to, Jeff. You can lead a student to a classroom, but you can't make me understand. No. I don't know if you guys remember, let me do a simpler example real quick. If I add x minus 2 is less than 1, then I can write that like this. You guys remember that? It's kind of related to squeeze. It's not really squeeze theorem, but it's just how inequalities act. I always think of this as the distance less than 1, so I want you to stay close to me. So here I am. I don't want you to get further than 1 that way or 1 that way. I always call this a sandwich, because I want it to be between -1 and 1, stay close to me, right? Okay. So what the shit? What good is this? Look at this. You cannot solve that, by the way. There's nothing to solve here. So what can we do with this? We can plot it. We can plot it in our calculators. And I did not get you ready at all. I had so much time this morning. Dooby-dooby-doo. What am I going to do here? Yeah. All right. I'm going to destroy school property.
Nice.
Burn it down. All right. Now, oh, this will turn on eventually. I like it. And again, this should be the weirdest part of this section. Because the other parts of it are just change elements. Old news. Okay, here we go. Okay, please tell me you work. Let's see. How about those Supreme Court hearings, huh?
I'm just waiting.
Hey,
Dude, the questions, man.
I love my.
Wait, what about the Supreme Court nominee?
Anybody watching the Supreme Court confirmation hearings?
Yeah, there's some pretty strange stuff going on.
Yeah, that's all we'll say. That's all I'll say. I was just trying to pass the time until this decided to wake up, and it is waking up. It's going to tell me. I don't want. Oh, thank you so much, though. I don't care. Thank you so much. Okay. I don't want you. Go. Just. No, I don't want that. Boom, 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 boom. There we go. Okay. Now. So in our, if you have your calculators, get them out. Get ready. So what I'm going to do is I'm going to plot this one and then this one and then this one. So y1, y2, y3. So y1, oh Jeff, there it is. X to the 1/4. Minus 0.1. Then I've got my approximation. 1 over 32 x, what was it?
Plus 3
3 halves. And then I got this guy, x to the 1/4 plus 0.1. Okay, let me stop for a minute. You don't need a calculator that can do multiple colors, but this kind of problem is easier if you do. So what's going to happen is, all right, let's see what happens. So everybody, has everybody got that in there? Just playing along? Everybody do this for me. Hit zoom 6. Dude, look at that. That's fast. I like that shit. Zoom 6. So let's all start off on the same page. Now, what's kind of like the most important X value to have show up on the screen? Think back to how we built this thing. We built this toilet. 16, yeah. Yeah. And right now, if you did zoom 6, you can only see up to 10. Let me stop for a minute. Is everybody doing all right? Just playing along? You got that showing up? So what I'm going to do, a couple things. I don't really care about all this stuff too much back here, right? So if I go to window, I can tell it. Let's start at -1 for x, and let's go up to 24. Why not? Just so 16 is in there in the mix, right? Okay, let's try this. So at least now I can see 16. Now, what's something else I could do? Any other unused space that's sort of like smushing things too much? Am I seeing up and down rational amount? So let's make my y max and my y min smaller. Let's kind of estimate what I want. I really want you to understand what I'm doing. And then I'll show you kind of a shortcut to this, but I want you to understand the window function. Maybe make y max 3. Do you see how that's going to capture and make y min -1? That's going to really kind of blow it up for me.
So what's the third function? 132x plus.
It's up on the board, but there it is.
Oh, right.
So let's go to window, make y min -1, and we make y max 3. Okay, now that's, oh, look at that. That kicks so much ass. Okay. I really want, now visually, what the shit does this mean? Can anyone tell me what you think that red line is? That's a line, right? So obviously, which piece is that? That's our approximation, correct? This is like the floor and the ceiling. When does my red line get between these two the first time? Like, is my approximation good back here? No, it's not between the allowed, it's not within the allowed tolerance, yes? So when does it first get between them? About right there. Can I see currently where it exits? So what should I do then? I gotta see further out, right? So let's make x max, I don't know, let's make it 40 just to be on the safe side. There we go. I really want this to visually make sense. This thing tells me I will be within 0.1 as long as this line is between this and this. So if I can figure out what the x value is here, and I can figure out what the x value is here, those are how far away from 16 I can get and still get a reasonable answer. Does anyone know what function in the calculator I can use to get this? Better than trace. Trace is approximately, I want exact. So go to, see right above trace it says calc. Don't I want to get the intersection between the red and the black line? Do you see how it intersect number 5? So right now I'm on the blue line, right? Looks like. So what I'm going to do, I'm going to hit the up and down moves between lines. Left and right moves left and right. It's amazing. So if I hit up, I'll jump up to there. So the quick way to do intersection, it's going to ask me 3 questions. All right, what is your favorite color? No, it's going to ask me, what's the first curve?
Would you really just have to make a Monty Python reference there?
Totally, of course. So call me Tim. So if I hit enter, let's see what it does. All right, it bounced to the blue line. Do I give a shit about the blue line?
No.
No. All right, so let me do this more carefully. Let's do this from the beginning. Hold on. I got 3 lines up here, so we'll for you. So everybody do this with me. Hit second, trace, and then do 5. Let's kind of start over a little bit. So let me move up. What line am I on right now? Can you tell? Y3. I love it. The black line. Y3. Can you guys see that even if you don't have color? Can you see that you're on Y3? Yes? Okay. So let me hit enter. Now it wants to know the second curve. If I hit up, that's still just the same curve I just did. I got to hit up one more time. Now I'm on Y2. So you got to feed it the 2 lines you want it to look at. So now I can hit enter because now I'm telling it that's my second curve, is the red line. And then it wants a guess, and the first thing I did was put it, my guess, so I'm just going to hit enter. So to be within 0.1 of the right answer, I can go all the way down to 6.7. That's crazy. And now you can do the exact same thing to see how far up you can go, right? So how would I change things if I wanted to only let it to be within 0.01? I would just go in and change that to 0.01 and change that to 0.01. That would smush my floor, my ceiling, and then I'd have So if I smush them, it would be like right here, maybe to right there. It'd be a lot less room for me to go. Okay. So in a sense, there's not much new. We're just using a tangent line more than we have before. But at the really same time, this is really huge. This is a huge step. This is the first step in fitting curves. And that's a big thing in Calc 2 is can I find a polynomial that approximates like sine x really well? You can't. Isn't sine x kind of look polynomial-ish, right? But the real problem is, wouldn't a polynomial eventually go forever somewhere eventually? So that's why you would need an infinite polynomial. I'll stop saying that. Stop. That's Calc 2. Okay. All right. I don't know. How do you guys? This is all brand new. But that's I think the weirdest part of this. And let me show you something real quick. If I do, I don't know. Oh yeah, let me do this. Zoom 6. Now let me change my x to -1 to 40. And look at this. That looks disgusting. Well, one of my favorite things is zoom box. Zoom box. So I can move this cursor somewhere safe, like right there. If I hit enter, that's the corner of a box now. So if I go up and over, then I go up a little bit more. Now it's going to zoom in. It's going to enhance. So that's shit. So zoom box is one of my favorites. Window is very detailed, but zoom box is like, I don't give a shit what the specifics are. I just need to see this part of it. So you just put a little box around it, bring it forward so you can see it. All right, so it's sort of like CSI, but real. Right. Enhance, enhance, enhance. Do you know how video works? Sorry. All right, so that's section 310. It is fundamentally finding tangent lines. That's what it really is. I will tell you one thing. Here's one thing that gets a little weird, and then I'll talk a little bit about 311, and then we'll get the hell out of here. Oh shit! I gotta remember you. My poor little camera. So let me give you one little thing that will throw this off a little bit. Oh god. Okay. So let's do like, let's do one that with trig function real quick. I like it. So I want to find a linear approximation that's that function that works around pi over 4. And then I want to use that, use the linear approximation to find sine of, you can do it, Jeff. You can do it, buddy. Pi over 12. That's nice and gross. I like it. Nice and gross. Okay. So this is a little bit different because of the fact that I have extra shit inside, and you'll see where you have to be careful. But can somebody help me out? What's the first step? So one first step I could do would be to write down just the general form, right? This is y1, this is m, x minus x1, right? This form is a little more useful because, like I said, it's more constructionist. What is f of a? What is f prime of a? What is a? And you put it all in. So what is f, and what's a? What is a? Pi over 4. Oh. So what is f of pi over 4? That's what I need here. Zero. Yeah, sine of 0 is 0. Is that cool? You guys all right? All right. What's f prime of x? Don't overthink. No. You're thinking ahead. I just want f prime of x, not f prime of the number yet.
Negative cosine x?
Not quite.
Or, no, cosine.
Cosine of, not x.
X minus pi over 4.
Yes. And is there a chain rule piece?
Yeah.
No,
Well,
because this slope is 1. It's linear slope of 1. I mean, what's the derivative of the inside? 1. Okay, so there's always a chain rule piece, but it's just 1, so it doesn't show up. Real quick. Don't write this down. Just watch this. What's the derivative of natural log of this? Okay. What's the derivative of natural log of x plus 7? 1 over x plus 7. Because I don't have to think at all, because the derivative of this is 1. It's slope 1. So the natural log of any slope 1 dude is going to just be 1 over that thing, because there is 1. Okay, so coming back to this. What is f prime of pi over 4? Because I need to know what f prime at a is. What's f prime of pi over 4?
Cosine of 1.
Cosine is 0,
Cosine of 1.
which is 1. I like it. Okay. So now I got everything I need. The approximation to this is 0 plus 1 times x minus a. So the approximation for sine of x minus pi over 4 is x minus pi over 4. It's crazy. Now, some of you guys might remember, as x gets really small, sine x gets closer to x. So I mean, that's basically what we just rediscovered. So how do I do this? Here's where you got to be really careful. Do I just put a pi over 12 in for x? Can somebody tell me why I do not do that? And we did that before, didn't we? But something is different here. If I want sine of pi over 12, if you make x pi over 12, is that what you get here? No. So what do you have to do first? You have to figure out what I want pi over 12 to end up in here, yes? So the first thing you got to do is figure out what x makes that happen. And that's what you put in. You see that? Why didn't we have to do that before? Because what was inside? X. X was inside. So how do I make it what I want it to be? I make x that thing. I'm done. Oh shit, there's not just x inside. So if I want pi over 12, I go, oh, okay, shit. How do I make x minus pi over 4? Pi over 12. 3 pi over 12 plus pi over 12, 4 pi over 12, and pi over 3. Did I do that right? I don't know. Right, LCD and blah, blah, blah. So I get y is approximately, sine of pi over 12 is approximately pi over 3 minus pi over 4, which equals pi over 12. Crazy shit. So the main point there is, I don't care what function I give you, it's all the same steps. But when you have to approximate something, you have to be careful. The x you plug in is what makes that show up. You don't just put pi over 12 in. You want pi over 12 to be what shows up here. You got to put the x value that makes it happen. Okay, maybe. All right. So quick word about 311. I'm not going to say too much here. 311, fundamentally, 311, I'm not going to end up throwing a lot of stuff from 311 at you. But I need to assign it. I need you to do the homework so you know that these things exist. But we're just not going to have enough time to really play around with them a lot, so I'm not going to feel like I should throw a lot of it at you. But what are normal trig functions based on? Don't say triangles. What are normal trig functions based on?
Unit circle?
Yes, circles, right? Sine, cosine, tan, all that crap is based on unit circle. And what's the equation of the unit circle?
X squared plus y squared.
Kick ass in a half. All right, 11. And that, of course, leads to the most fundamental trig identity. Sine squared plus cosine squared equals 1, right? Okay. Here's where things get interesting. This is your first taste of something that you would never think about. I can construct, in fact, not me, it has been constructed, a whole trigonometry set based on hyperbolas instead of circles, right? So what, could you base one on squares? Yes, you can. You can look it up. You can look up trig functions based on squares, based on unit squares, right? If you don't want to, I understand. What is the equation of a hyperbola? Does anybody remember? Isn't a hyperbola like a circle that went nah-eh? Like, I don't want to look at you no more. You just turn. Yes? So it should be a lot like that. Think about it real quick. Oh, there's so much to this. This is how I teach my calc, my pre-calc. If I add two things together, two positive numbers to get something, isn't it kind of constrained? Like, give me two positive numbers to add to be 4. In fact, let's make it integers. Give me two integers that add to be 4. 2 and 2. Keep going. 3 and 1. In fact, let's I said positive integers, right? Okay, good. Two whole numbers. 0 and 4. 4 and 0. 1 and 2. 1 and 3, whatever. Isn't it constrained? Give me two positive numbers, integers, that subtract to be 4. 5 and 1, 6 and 2, 7 and 3, 8 and 4, 9 and 5. How long could I go? For frickin' ever, right? Doesn't that, do you see how the picture captures that? Constrained, can go forever. These can't get closer than 4 though, whereas these have to stay, well, within 1. I made it 4 just to make it easier, but you guys understand what I'm saying? So this equation is this, because of what we just said. So in hyperbolic trig, get this, hyperbolic cosine minus hyperbolic sine is 1. The same way that in unit circle trig, cosine plus sine squared is 1 because it's based on circle. And hyperbolic, it's based on hyperbolas, incredibly enough. Little h, so we call this affectionately cosh in sinh. So then I got tanch and secich, sinh, cosich, cotanch, because we're weird. Now, here's the last thing I'll say about this, and then we'll get out of time. Yeah, not too bad. Let me see if I remember this. Is it plus? Let me see if I got that right. No, so of course it's minus, Jeff. You got that all wrong. It's the cosh that is minus. Plus. Now that does not jump out at you from what I've discussed so far, correct? So on one level, so you could prove this easily, given that, yes? You just square this guy, square that guy, take the difference and show that it's 1. You could actually do it. It's not that hard. Why is it exactly that? Well, what's interesting about this whole thing is you can derive a few different possibilities, but we want, this kind of thing shows up so much in mathematics that we wanted to package this as a single thing. So it just, on one level, it just makes it easier to write answers to certain things. Instead of having a bunch of e's running around, I could just say cosh y or something. Cosh squared y or tangent y, whatever, right? What do you think tangent y is? Yeah, you would hope it'd be sinh over cosh, right? So that's exactly what it is. And so that would just be, the 2's would cancel, you get e to the x minus e to the x over e to the x plus e. Right? Would derivatives be difficult to do? Because they're freaking based on exponentials, which are the best things around, right? So in this section, you will be asked to use these, you'll be asked to do derivatives. I'm not going to make you memorize this, but you will do the homework, and you will know the hyperbolic stuff exists. And one of the most immediate uses for hyperbolic functions is if you put a line between two poles, it creates a certain shape. It's basically impossible to make it straight. And the shape it takes on is called a catenary, because of course it is. And the only function that you can use to describe the shape is a hyperbolic Trig function. Yes?
Is there like trigonometry, but like 3 dimensions?
Of course.
You know, I think it's
I was like, damn, that's crazy.
Well, what that really fundamentally entails is just adding more variables to represent angles between things in 3 dimensions instead of just 2. So it's not like you're not going to add like new sine, cosine, and now we have flumba and coflumba. No. But it's just the angles that you define are what's important. Yeah. And if you get to Calc 3, Calc 3 is all about calculus in 3 dimensions. And well, actually, sometimes in just more than 2 dimensions. So possibly 87 dimensions. But
That's what volume is, right? The third dimension.
what's that?
That's what people volume is, like adding to the third dimension.
This is what the, I'm sorry.
That's what hopefully volume looks for, right?
I'm really sorry.
That's what volume looks for, right? Like,
What body?
no, volume.
Oh, volume.
Yeah.
Oh, I'm sorry. Yes. Thank you. I'm sorry. I just couldn't make it up. Yeah, so in Calc 3, you develop some nifty ways to, well, Calc, in this class, we're actually going to do volumes of things. But we're going to do it in a way that makes it 2-dimensional. And you'll see when we get there. But when you get to Calc 3, you could do more freaky volumes because you truly live in 3D in Calc 3. So yeah, you'll be able to do a lot more volume stuff in Calc 3. We're going to be very constrained with, our volumes are going to be take a shape and then rotate that shape. Yeah. Because that's the only thing, the shape lives in 2D, and then when I rotate it, I can do some nifty stuff to make it an interval. Well, you don't know the word interval yet. We'll get there. Okay, that's all I want to say. That's plenty. Who didn't get their test back? So how many, we ended up with 1, 2, 3, 4, 5, 8, 9, 10. What did I say? I said 9. We got double digits. Nobody won. Too bad. All right, guys, have a good spring break. And I'll do what I can.